And I'm going to tell you something that's bizarre. And I imagine if I were listening, I would simply not. I'd just check out, I guess. Okay, but maybe maybe you'll follow this. It turns out scientists in the late 19th century, right? That's the 1800s, struggled with understanding the light that was emitted from atoms and molecules. It was weird. When solid liquids or gases are heated sufficiently, they radiate some of the excess energy as light. Now, photons produced in this way, so if you take a solid liquid or gas and you heat it up, you're going to get some of that energy out as light, right? When you and you know that if you've ever seen a stove top and you heat the top up really hot, maybe you've never seen something like that. It turns a color. Or what about if you put a poker in the fire and you heat an iron poker up really hot? It turns red, right? If it gets hot enough, it's going to be white. Well, that's energy being radiated as light. So photons produced in this manner have a range of energies and thus produce a continuous spectrum. That means that they can be really any color. That's what that means, okay? Now, in contrast to continuous spectra, light can also occur as discrete or line spectra, having very narrow line widths interspersed throughout the spectral regions. This is surely going to make no sense until we see a picture, okay? In other words, you're not going to have light of just any old color coming off of particular experiments, okay? So, for example, exciting a gas at low partial pressure using an electrical current if the gas is not dense, right? Just a few more particles of gas in this. I'm sorry for my voice. I'm feeling like I'm fighting this here. Exciting a gas, very small amounts of gas in the chamber with electrical current or heat will produce line spectra. What does that mean? Each element displays its own characteristic set of lines. And this really befuddled scientists in the 1800s and the early 1900s. They were like, this does not make any sense, okay? With their current understanding of physics. Did not make sense. So here's a picture from your textbook. Neon signs operate by exciting a gas at low partial pressure using an electrical current. This sign shows elaborate artistic effects that can be achieved. All right, so you have some gas in here, in this like star, this purple star, some gas in there, and they put electrical current across it, and it emits a purple light. Weird, right? Orange, green, white. Okay. Now, each emission line consists of a single wavelength of light, which we'll talk about more in just a second. I got a picture coming up. This implies that the light emitted by a gas consists of discrete energies. Weird. The origin of discrete spectra in atoms and molecules was very puzzling to scientists, and it produced lots of arguments. According to classical electromagnetic theory, only continuous spectra should be observed. Okay? So, again, in the early 1900s, scientists are going, this is bizarre. They didn't believe the results, didn't believe it. And it turns out there was a new paradigm that was waiting for us below the surface, okay? And it's called quantum mechanics. All right. So anyways, look at this. If you take sodium and you heat it up, sodium vapor, sodium gas, which sodium's typically a metal, right? So you're going to have to take a very, very low amount of it. Sodium vapor, and you heat it up, you get lines that look like this. 2 blues, a couple yellows, a couple more yellows, and a red or orange, okay? If you take a hydrogen gas, you get something that looks like this. Purple, blue, blue more, so I guess more like cyan, right? And red. If you take a calcium gas, you get this. If you take a mercury gas, you get this. This is bizarre. Utterly bizarre, right? And it's very characteristic of the atom itself, of the element, okay? So in 1885, Johann Balmer, near the end of the 1800s, Johann Balmer was able to derive an empirical equation for hydrogen, only for hydrogen, okay? The equation related the 4 visible wavelengths of light. Let's go back to hydrogen, look at those again. You see, here's hydrogen, right? Purple, I guess violet, right? Bluish, light blue, right? These 4. He took the wavelengths of those, and he said, here's my wavelengths. If I set my wavelengths up, and I let n be 3 or 4 or 5 or 6, I can show an equation that will give those wavelengths, right? And it's going to be some constant in there, K. Just some constant K. This is very clever. Okay, these guys were really interested in this and really dedicated. You don't just get this by following, by completing your assignments. You get this by looking at the data and saying, what is going on here? What is going on, right? So congratulations to Johann Balmer, and I really thank you, Mr. Balmer, for doing this for us, because it's surely was a real puzzler, and I think extremely clever. All right, so here's the Balmer series, right? You can write this down. You can put this in your notes. It's going to show up again, but yeah, but I would never expect you to have that memorized, okay? So then Johannes, I guess, Rydberg generalized Balmer's work and said, he developed an empirical formula and said, okay, I think if this is Balmer's work, I think I can generalize this and say that 1 over the wavelength of light for hydrogen can be split up like this, right? Where we have two ends, an initial n and a final n. And we're going to talk more about this, okay? But then figure this constant will be called the Rydberg constant, and its symbol is R. It looks like the universal gas constant, but it's not. R with an infinity symbol right there, right? And this constant is here. You would never have to know that, right? We can always look this up, okay? So, and yeah, this is a generalized formula for Balmer's work. Okay, so this is our introduction to line spectra, and we will be talking more about this in upcoming conversations.